Namaskaram. In last class, we have seen the linear combinations in a vector space. In this session, we will discuss about spanning set in a vector space. Okay, this is the definition of a spanning set. The set of all linear combinations of a finite set of vectors S is equal to V1, V2, etc. Vn is called span of S and denoted by span of V1, V2, Vn or span S. Okay. So, what is the meaning of this representation? This means tan of S is equal to set of all possible linear combinations. What is our linear combination of V1, V2, Vn? That is nothing. C1, V1 plus C2, V2 plus etc. plus Cn, Vn, where these Ci's are any scalar, arbitrary numbers. Okay, that's why Ci belongs to R for all I. So, by choosing different combinations of C1, C2, Cn, we have different elements in our spanning set. Okay, so it is clear that the spanning set contains automatically all the vectors, because if we choose C1 equal to 1 and all other scalars are 0, then that means V1 also belongs to S. So it is clear that our S is a subset of span of S. Clear? And span of S contains more than that, because we have a freedom to take all the linear combinations. Okay, let's see some examples. Determine the span of 1t square. And it is clear that these three elements 1t t square belongs to which vector space? Yes, they are all belongs to our p square. P square is nothing. P square contains all the polynomials up to degree 2. We know that that's a vector space. Okay, and we have to find the span of these elements. Okay, that means this is our vector space p square, and we consider a set that will be S. S is equal to 1t t square. It's a three element subset of p square, and we have to find what is the span of S. Okay, so what about the span by definition? Yes, span of S is equal to, by definition, set of all linear combinations of these three. That means what? C1 V1 plus C2 V2 plus C3 V3. Here V1 is our 1, and this is V1, this is V2, and this is V3. We have only three vectors, right? So that's why you consider C1 V1 plus C2 V2 plus C3 V3, such that C1, C2, C3 are real, any real numbers. Okay, because we consider only vector spaces over real numbers. And this becomes C1 plus C2 T plus C3 T square, where C1, C2, C3 are any real numbers. So what about this collection? This collection contains set of all polynomials up to degree 2, right? Because if suppose you choose C3 equal to 0, then what happened? Then this collection contains all the first order polynomials, right? Similarly, if you keep our C3 equal to 1, then this collection contains set of all second order polynomials. Similarly, you can generate everything. Suppose C3 equal to 0 and C2 equal to 0. Then this contains all the scalars, because we can choose any CA, right? So this is nothing. This collection represents all the polynomials, including our scalars. Scalars are nothing. Scalars are also polynomial. We can visualize scalars as a polynomial of degree 0, right? Anyway, this collection contains all the polynomials up to degree 2. That is nothing. That is our P2. So span of S is equal to P2. This is a very nice idea, because P2 contains infinitely many elements, right? This P2 contains infinitely many elements. But we can generate the same P2 using a three element set. It's a very nice idea. Good idea. So that means we can represent this P2 using these three elements, right? Suppose we consider another element from arbitrary element, some 3t square per 4t minus 5. You can generate this element using this small set. Similarly, you can generate any element from P2 using this small set. That is the concept of spanning. So the spanning set, we can visualize this spanning set as a representative of a vector space. You got it? Yes, this spanning set is P2. Next problem. Determine the span of 1, 0, 0 and 0, 1, 0. It is clear that these two vectors are from which vector space? Yes, it is clear that these two vectors are belongs to R3. That's clear. So R3 is our original vector space, and these two vectors are elements from this vector space. So our subset S is nothing. S is a subset of RQ. Okay, we have to find the span of this set. By definition, what about the span? Set of all linear combinations. What is that? Yes, by definition, span of S is equal to C1 into 100 plus C2 into 010. Okay, this is our V1 and this is our V2. We have only two vectors. So C1 V1 plus C2 V2. Set of all C1 V1 plus C2 V2 where C1 and C2 are arbitrary. So this becomes C1 comma C2 0 and C1 and C2 arbitrary. So what about this collection? Set of all C1 C2 0 where C1 and C2 are arbitrary. That means this x coordinate can take any value, y coordinate can take any value, but z value is always 0. Z value is always 0, right? What is this? What is in 3D? Z equal to 0. Yes, Z equal to 0 represents a plane. Which plane? XY plane. Yes. So we can identify this spanning set with our XY plane in our three-dimensional space. Clear? So geometrically, the span of this two element set is nothing. It is our XY plane in 3D geometry, 3D space. Okay. But anyway, this set can't generate our entire set R3. Right. Actually, these two members from our vector space R3. But in this example, the span of S is not equal to R3, right? Span of S is not equal to R3. It is only a subset of R3, right? But anyway, we know that this xy plane. What is xy plane? What is xy plane in terms of our coordinate system, coordinates or in terms of Rn? Yes, we know that xy plane is nothing set of all ordered pairs, right? Xy plane means set of all ordered pairs. That is what? That is nothing our R2. And we know that this R2 is a vector space. So anyway, the span of this S, span of this set is not our entire vector space, not entire vector space R3, but again its span is a vector space. It's a very nice property because these two members from R3, its span is only like C1, C2, 0. So this is not equal to R3, not our entire vector space, but the span is XY plane. So we know that this XY plane is a vector space. That is another property of spanning set. Whatever be the collection, the span is always a vector space or subspace. Here we can say that actually suppose this is our span. Span always contains S. So if this is our span of S, then we know that span is always a subset of R3. Okay. Not only that, the spans are always a vector space. That is called a subspace. Okay. So we can easily show that the span of S is always a subspace of a mother vector space. Clear? Even though it is not full space. Okay, that is our theorem. The span of a set of vectors S is equal to V1, V2, etc. Vn in a vector space V is a subspace of V. Subspace means it is a vector space, no doubt. Only thing is that vector space is a subset of a bigger vector space. That's all. Okay. So this is our graphical representation. This V is a vector space and S is a subset. It's a finite set, subset of this vector space V. And you think about the span of S. What is span of S? That means set of all linear combinations of members of S. Okay, we know that it is it's a bigger set, bigger than S. And sometimes the span of S may be V, sometimes it is V. Whatever be the span of S, it is V or subset, no problem. This big set, this yellow set means span of S. That is always a subspace of V. Subspace means it is itself a vector space under the operations of V. Clear? We can easily verify this result because we have to verify only two conditions. What are the two conditions? The first one is if we choose two elements u and v from the span of S and check whether u plus v belongs to S. And what about the second condition? To verify subspace, you check whether alpha u also belongs to S. This is u. If u plus v and alpha u belongs to S, then we can say that S is a subset, not S, sorry, this is span of S. This span of S. Okay, we have to check whether this span of S is subspace or not. So we consider two elements u and v from span of S and check whether some belongs to span of S and alpha u belongs to span. Okay, you can easily verify. What about u and v? What about u and v in span of S? Okay, in general, we take an arbitrary element u from our span of S. We know that span of S contains all the linear combinations of these vectors. So whatever be the element u, it is always of the form linear combination of these vectors. That's why I choose u as some a1 v1 plus a2 v2 etc plus a n vn. Similarly, we also another linear combination of these vectors because we also belongs to the same span of S. So we can take it as b1 v1 etc b2 v2 etc plus b and vn. Then next we have to check whether u plus v belongs to span or not. These two vectors belongs to span of S. What about u plus v? Yes, by definition of vector addition, u plus v is nothing. A1 plus b1 times v1 plus a2 plus b2 times v2 etc plus an plus bn times vn. And what about this one? Is it belongs to span of S or not? Yes, it is belongs to span of S because this is again a linear combination of the vectors v1, v2, etc. vn. That's why because a1 plus b1 is a scalar, a2 plus b2 is a real number. They are all scalars. Okay, it is clear that this is also a linear combination. That's why this belongs to span of S. So what is our conclusion? If u and v from span of S, then their sum is belongs to span of S. So it satisfies the first condition. Similarly, you can verify that alpha dot u. Okay, alpha is any scalar and u is, you can choose u as like this. Then what about alpha u? Alpha u like alpha a1, b1, etc. plus alpha an, bn. What about this one? Yes, this is also a linear combination of the same vectors v1, v2, etc. vn. So this belongs to span of S. So it satisfies both the conditions. So it is clear that span of S is a subspace of a vector space V. Sometimes this span of S may be V. Okay. Okay. Another important property of our spanning set is the span of S is the smallest subspace containing S. Okay. From this graphical representation, it is clear that we have a vector space V and we consider a finite set S, it is a subset of V. And you think about the span of this vector, span of this set S. And now we know that this is a vector space. This span is a vector space or subspace, whatever be. It's a subspace containing S. Not only it is a subspace, it has one more property. It is the smallest such one. Right. The span of S is the smallest subspace containing S. Okay. That's another important property of spanning set. You can easily verify this result. Okay. The basic idea of this concept is our vector spaces are always closed under linear combination. That's the main concept of this result. Okay, anyway, that's it about our spanning sets. In next session, we will see the concept of linearly independence. Okay, thank you.